Hey, good morning, gang. Hope you guys are doing well. It's Tuesday, um, and I just thought I'd introduce things to you live this morning. I didn't get a chance yesterday to get back to you. What I've done is I prepared a learning page for you today, which hopefully will take you through both today and tomorrow. Yesterday, if you took a look, we were starting to learn about pendulums and simple harmonic motion. If you haven't yet, make sure you do that reading on Physics Classroom. That's a good way to soak things in if you're a good learner through reading. I'm going to just highlight some of the main ideas you should have gotten out of the reading here real quick for you. I put together a very good learning page today in the Simple Harmonic Motion folder. It's our day 2, kind of our last day for Simple Harmonic Motion. And then you can also have tomorrow to wrap up the little worksheet that I've got for you today and these ideas. So Thursday, we'd like to take just a little quiz on Schoology on it and then move on to our next topic, which would be waves. So it's a little 3-day unit, Monday, Tuesday, Wednesday on simple harmonic motion. So there won't be anything new on simple harmonic motion tomorrow. It'll just be wrapping up what I've got for you on that second learning page. Okay, I might highlight some more of the big ideas, and I'll be available for questions and things like that. But that's kind of where we're headed for the week, just so you have a connection with me here live and kind of understand what the expectations are moving forward. So simple harmonic motion is important. Really, if you take a look up above here, what it means is the vibration of matter. So far in the course, we've said physics is really all about how matter moves in the universe and the properties that affect the motion of matter. It's what everything is made up of in all the different systems that we live in the universe. And so we've talked about linear motion, right? That's how we started out last term. We did projectile motion under a constant force of gravity, saw that it was a parabolic shape. Simple harmonic motion is an interesting motion in matter. It's really almost more important in a certain sense. Most of the information we take in around us starts with a vibration. My voice right now, my vocal cords are vibrating so that the information can be transferred to you. Your eardrum vibrates and sends electronic signals that are kind of oscillating in a way into your brain, and then you can make meaning from that. Light comes to us from the universe into our eyes in the form of a wave that has to start with the vibration of a charged particle somewhere. So much of the universe around us, if you've thought about it or not, comes to us from the beginning of the vibration of matter. So that's why it's an important fundamental principle to begin to understand. So the simple part of it means that the matter is obeying some very fundamental properties. Okay, so that's the only kind of vibrations we're going to start looking at right now. And if you ever wondered what sines and cosines were for in math class, they model simple harmonic motion, a system that repeats itself in a very regular pattern over and over and over again, in this case as a function of time. Okay, so that's what simple harmonic motion is simply a vibration of matter under certain constraints. Now, two systems that are very easy to use to start to explain simple harmonic motion was the ones you were reading about yesterday. So for instance, you could have a pendulum, all right? So a pendulum is going to swing back and forth about an equilibrium position. The equilibrium position is 0, right? If a pendulum is going to be straight down, you'd have the cord upwards, you'd have gravity downwards. There's no forces that would make it naturally swing. You have to pull it over to the side, and then there's a certain part of gravity, right, that acts to bring it back towards an equilibrium position. So when you displace it from equilibrium, there's a component of a force along the path that tries to center it. And notice on the other side, that component of gravity would reverse itself to try to center it. So a centering force of a system is one of the elements that makes a system simple harmonic motion. That's called the restoring force, and the restoring force is to try to bring it back to its equilibrium position, where the force is 0 at that point on the object. The net force is 0 on that point at the object. All right. Another one is a spring. So we could think of a spring that's hanging in equilibrium that has a mass just sitting on it, and it's just sitting there at rest. And if you stretch it downwards from its equilibrium position, right, we could call that position 0, it's gonna fly back upward, and it's gonna come back up to some position here from some position it started from down here, and it'll oscillate up and down about that equilibrium position. Okay. So two things that these properties, that these systems would have in common is that they would have a maximum amplitude from equilibrium to the right, or to the left, and that they would have a continuous period of vibration, T, that is going about the central point like that, a time that Sorry about that. My dog was causing a little bit of trouble there. Okay, so we've got the amplitude of a system about the equilibrium point, both for a period and for a spring system, and so that, of course, what you were reading from yesterday would be the time to make one cycle. Okay, and so the time to make one cycle, right? We use like capital letter T, and the unit is just going to be what we're used to thinking about as the second. And that period, you could also describe how frequently the object is moving. And these two are inverses of each other. So the period is 1 over the frequency, or the frequency is 1 over the period. And so for frequency, the units would be inverse, right? It's going to be cycles per second rather than this one being seconds per cycle. Okay, how long it takes one cycle to happen. The frequency is going to be in cycles per second. Okay, that's going to be the unit for frequency, little letter F. And sometimes that's called, you'll see it in your reading, they call that Hertz after a scientist whose last name was Hertz. Okay, so Hertz is a cycle per second. So you can just convert between the two by doing the inverses. Now, something special about simple harmonic motion is that this restoring force has to be proportional to the distance you pull it back. So the farther you pull it back, the stronger the force is, so it returns it more quickly. You'll notice that for both systems, the amplitude is not going to be in the period formula. All right, because if you stretch it further down, the spring force is stronger. So although it has to cover more overall distance, the force here is greater, so the acceleration will be greater. So it'll start off with an overall, it'll reach an overall greater maximum speed coming through here. So even though you stretch it farther back, since the average speed is going to be like greater at any given point, like coming through the midpoint or whatever, it covers that greater distance in more time. Amazingly enough, those effects balance out so that the period is not affected, both for a pendulum or for a spring system. So it's pretty easy. I won't go to the formal derivation for this right now, but the period for a pendulum goes from 2 pi, that it goes through 2 pi cycles in a certain time period, right? It repeats itself over and over again, just like a circle would repeat itself over and over again. And the two physical parameters that a pendulum depends on is its length in meters. Okay, you got to make sure you're in meters, and the gravity constant of the planet that you're on, right? So notice that it could be the Earth, the Moon, or whatever. The period would be different, but it doesn't depend on the amplitude of the pendulum. As long as we're at small angles, it works pretty well. In a spring system, the period of a spring system is very similar then. Okay, simple harmonic motion objects will all have this same form. But for a spring, it doesn't really depend on its length or gravity, right? For a spring, what it depends on is the mass that you're trying to oscillate back and forth and how stiff the spring is, the spring constant. Okay, so both of these two systems are the fundamental ones people study when they first begin learning about physics. All right, so from there, I just want to show you on the learning page, the worksheet is going to have some different graphs and things to make, and I wouldn't expect you to know how to do those just straight off. So what I've got here for you on the learning page is, again, just how would you use the simple pendulum formula to make sure that you're able to use that. I think the videos yesterday probably did a pretty good job of that. How can you use the period dependence for the mass of a spring and the formula and how that kind of works out. Okay, and the system's there. So rather than recreate videos like this, these have been done very well. So I think these should work out very well for you to give you a visual explanation of simple harmonic motion. And then down here, this explains the graph part of the worksheet that's attached at the bottom of the page. Okay, and so you can either print that worksheet out and draw on it, or sketch it on notebook paper, however you would like to do it. And then we'll turn those in, Thursday sometime before we take the quiz. All right. So you'd want to watch this video for sure before you start to make and try to draw the graphs. And then this simulation right here is very good. Okay. It pretty much gives you almost the answer to the graphs because you can see over here, it'll make them for you. So if you click on that, if you click on the simulation down here in the lower left, it'll run the system. You can change the parameters like the spring constant, the mass of the block, and you can take a look how the shapes of the graphs go. And think about at each place, like in equilibrium, the velocity is a maximum, but the force would be a minimum, right? And so that would have an effect on the acceleration because F equals ma. So think about where the position is in its cycle, see what the velocity would be like in its cycle, see what the acceleration would be like in its cycle, right? Even though it's not moving out here, it'll have maximum acceleration because that's where the spring force would be a maximum, right out here when it's stretched the most. Same thing way over on the other side, the acceleration would be positive in a maximum because that's when the force, the spring force, is going to be the greatest, pushing it forward. Remember, at equilibrium, the force is zero, so you would expect zero acceleration at the equilibrium position. So this should help you try to get an eye on those graphs on how to do it. All right. Here's another one on how to calculate spring formula, so you can see one like that. But there should be enough for today and tomorrow to get you going. And again, I'll be available for questions, and I'll try to have a Google Hangout today and tomorrow at the regular class times I was doing last week as well. All right, I hope that helps, and I hope that's enough. I think it's more than enough for both today and tomorrow. So I'll talk to you guys later. Bye.